Welcome to my nightmare.
I'll snag a random local video sitting on my computer and drag it into Google Chrome. Lucky me! The browser renders the video, which kicks off playback right away. I spot a lone video tag nested inside body, where my videos lives. In the network tab, there are a few requests to my file. The first one shows no size and sits in pending status. Every time I scrub to some random spot in the video, another request fires off. My next burning question: if I want to catch the last 10 minutes of 3-hour Scorsese crime thriller in 4K Ultra HD, do I really have to twiddle my thumbs while the previous 2 hours and 50 minutes downloaded before I even start watching? The verdict? Probably not, but only if the site you are watching has put some smiggle of effort. Let's make a real-world internet test. I have uploaded a video to Cloudflare and cracked it open via link. The browser fires off a request, the server spits back at 206 partial content status, and over a few minutes we watch the downloaded size creep up. If I click on some random spot far from the current position, the previous request gets exit and the fresh one spins up. The ability to fetch any random chunk of video is achieved through these headers: request, range, bytes, response, content range, bytes. In plain English, the browser tells the server exactly which slice of the file it needs. Servers that support this advertise it with accept range bytes and respond with 206 partial content, plus a content range header describing the selected span and total size. The request can also pack an if range header with e-tag or last modified date, enabling validation. Is this still the same video file I start watching? If the server doesn't support partial downloads, it has to catch up the entire file. In that case, the response would not include a content range header. The content length header in a partial response will report the size of the specific chunk, not a whole video. The content type should match the underlying media file type. How do you enable range support on your own server? If you are generating something or downloaded it on the fly from elsewhere, implementing range support can be a gnarly beast, but it's doable if you have basic seek capability in the data stream. Range support and compression. If the server applies content encoding, for example gzip, to the response, byte ranges refer to the encoded bytes, which typically tweaks seeking expectation for media files. Most servers therefore disable response compression for byte range media requests. Nginx, for example, support everything out of the box with zero extra config, of course if compression is disabled. .NET, if you use static files, everything is baked in both IIS and Kestrel servers. But if you are returning media file via API endpoint, you should explicitly specify that range support is enabled by setting this parameter in results file method. If you are passing a stream, CanSeek might be true, which might not be the case for a boatload of different streams. Also ensure you set the correct content type. Example, video MP4, video WebM. Static file middleware in ASP.NET Core already handles range request with accept ranges byte and 206 responses when the client sends range header. But what about browser support? How video is stored boils down to two aspects: codecs and containers. A codec is a specialized software or even hardware that handles encoding and decoding video and audio. To decode video, you need to know how it was encoded and have the matching software or hardware. A container is how the video, file or stream is organized, since we need to cram video, audio or even several audio tracks, plus some metadata required for decoding, into a single file or stream. More than one approach to storing this mess emerged. Adding to the confusion, codec names and container names sometimes overlaps, sometimes not, and some containers support more than one codec. There is a smorgasbord of video codecs that squash video using various principles. Compressing video is a literal necessity because raw video won't squeeze through any internet pipe or wouldn't fit any reasonably sized hard drive. Here is a quote from Mozilla Developers Network. A single frame of high-definition video in full color is more than 8 million bytes. At a typical 30 frames per second frame rate, each second of Full HD video would occupy like 250 megabytes. A minute of Full HD video would need almost 15 gigabytes of storage. A fairly typical 30-minute video conference would need about half of terabyte of storage, and a 2-hour movie would take almost 2 terabytes of storage. The most efficient, widely available codec today is AV1. Modern Chrome, Firefox, Edge support AV1 in software and increasingly with hardware decode. Safari is catching up. Older smart TVs and embedded devices may lack AV1 support or hardware acceleration, so H.264 AVC remains the compatibility baseline, with H.265, also known as high-efficiently video codec, commonly used on Apple platforms. And now about containers. No, not Docker containers. Not all common containers are browser-friendly. For instance, AV is not supported. MKV is mostly not supported via HTML video tag. Right now, WebM is a great choice. VP8, VP9 or even AV1 video with Opus or Vorbis audio are supported in Chromium-based browsers, Firefox. Safari's support of WebM is limited and version dependent, so MP4 with H.264 AAC remains the safest fallback. For adaptive streaming, HLS or Dash, fragmented MP4, typically FMP4, is a typical container. But what to do with videos that use another containers or codecs? Typically, we transcode them using FFmpeg. That's what the next video would be about. How can we add support of legacy browsers? You can store videos in multiple formats, something more convenient for modern distribution that sips storage and bandwidth, plus something that will be actually fire up for on TVs rolled out in mid-10s. Order matters. The browser will try source top to bottom and pick the first it can play. Including correct type attributes help the browser make faster decisions. How does YouTube encodes? YouTube supports mind-boggling array of platforms, so every video is stored on heap of versions, which are then distributed across thousands of servers packed right inside ISP networks. Among other things, it's this avalanche of versions that makes full processing after uploading to YouTube takes a good chunk of time. A ton of magic hides behind this little toggle. It follows magic twice over. If you snoop on the network tab while watching YouTube video, you'll see a flurry of tiny requests. What does this buy for you? It lets you avoid keeping connection alive for ages, like what happened when transferring one massive file throughout the entire viewing session. This allows a single server to juggle more clients. Also enables that some after switching. When the client realizes the video is choking, it can request the next chunk in lower quality. What does this demand? It demands storing video on the server not as one hulking file, but as chunks spinning a few seconds or even less. There are two standards for this: HLS and Dash. HLS is HTTP live stream, a format from Apple. It proposes chopping video into short segments, TS files, and a manifest describing how to stitch them back into a coherent video, M3U8 manifest. Literally a text file listing TS files. It is native to Safari and Apple gadgets. To support quality switching, you transcode the video to multiple ladders, bitrates, resolutions, provide a manifest per variant and a master manifest listing all variants with codec and bitrate metadata. Segment containers are typically MPEG-TS or FMP4, M4S files. Dash is dynamic adaptive streaming over HTTP. Conceptually, they are identical, but the manifests are in XML. The format is newer and expressive. Manifest can carry detailed codec, timing and segment info. Segments are commonly FMP4 files. You would ask, why are segments have different lengths? All modern codecs have the concept of a keyframe. We need to pinch pennies on a storage and bandwidth, so we describe groups of frames not individually, but as deltas from a keyframe. How to describe these deltas so they don't balloon larger than individual frames? And how exactly to pick these frames? That's precisely the playground for fiendishly complex innovations that happens once a decade or so in codec world. We don't need to sweep this right now. The key concept here, because keyframes exist, its advantages to slice segments precisely on them. So, how does YouTube actually rolls? They are reading the bleeding edge, so beyond chopping video into segments and storing multiple quality levels. They also fetch in smaller chunks within segments. Typical segments are from 2 to 6 seconds, but clients can request subpart ranges, enabling faster startup and more responsive adaptations, sometimes on the order of tenths of second. This lets them serve chunks to the client even faster, meaning the connection stays open for a blink. But a recon, what's even more crucial, video starts playing insanely fast. If you are viewing this video much after its publication, something can change. Netflix or Pornhub can cook something even more delicious in video delivery. One more trick that I like from YouTube is its immediate timeline preview. I absolutely adore this feature for precision seeking with instant frame previews. How did they pull it off? It is an old trick dating back to classic game development. They pre-generate frames from every second, or more or less frequently, pack them into a grid on a single image to avoid hammering the network with requests and to get snappier feedback for small mouse movements. Actually, they don't pack it into one image for long video, it can be many. But each such image will contain a bunch of frames for display. Another amazing trick from YouTube is hover preview trick. This trick again bunch on pre-generation specifically teeny animations in WebP format or short MP for WebM clips depending on platform. Historically it was GIFs, but they are not so efficient. So what are our next steps? First one is to develop a platform where we will allow users to upload only videos that can be played in browser with no transcoding. The medium mode is to transcode the videos from not supported containers and codecs to something that are supported by browsers. For example, encode AVI or MKV to something like WebM. The next step is to encode a video in multiple resolutions and bitrate and allow user to select preferable resolution. Then we will go even deeper and implement adaptive video streaming with HLS or Dash, generating these tiny chunks and manifests. Almost pro level would be to upload these chunks to the CDN to make it deliver even faster to end user. If you are develop some enterprise solution or solution for creators that want to distribute their videos safely without making them publicly available, we should add some authorization to it. And as a bonus, we will update our transcoding model to distribute the load between dozens of cloud machines. So, let's go.
Welcome to my nightmare.
Welcome to my nightmare.
Think you're gonna